Hello, and thanks for attending my session. Today I will talk about supercharged search with semantic search and vector embeddings. A little bit info about me. My name is Giorgi Dalakishvili. I'm a C# and .NET developer for about 17 years. I have worked with various relational databases. I also maintain a couple of open source projects on GitHub. So if you use Entity Framework Core, I suggest you check these projects. I think they will be interesting for you. So let's start with our today's topic. I will talk about semantic search, vector embeddings, and vector databases. So first of all, what is the difference between the traditional search that is called lexical search and semantic search? The lexical search returns results based on exact matches of the words or derived words that the user enters, while in case of semantic search, the search results may not contain the exact terms and phrases and words that the user entered, but the search results will match on the semantic meaning of the search query. It may or may not contain the exact words that were entered in the search system, but the results will match on meaning. For example, if the user searches learning how to use a database, one of the results can be SQL crash course. It does not contain the exact words that the user entered, but it matches based on the meaning. So what are the benefits of semantic search? One of the benefits is that it can distinguish between phrases that contain same words in different orders. For example, chocolate milk and milk chocolate. These are two very different things. One of them is a flavor of chocolate, and another is a drink with flavor of chocolate. So the semantic search can distinguish between the meaning and what the user wanted to search for. It's also easier for the users because they don't need to remember exactly the terms that you use in your database on your website. They may not remember the names, they may not know what words and phrases you have used to describe the items in your database, but they know what they are searching for. They will type what they want, and semantic search will be able to return the results based on the meaning rather than based on the exact words. So it is more user-friendly, it's more natural, and it's similar to the real-life experience when you go to the shop and you ask the consultant what you want, and the seller will offer you the items that match the items that you described. So how does the semantic search work? It's based on three main components. It's large language models, or LLMs, vector embeddings, and similarity metrics. So LLMs are trained on a vast amount of data, and they understand the context and relationship between the meaning of the sentences. And they are the foundation for capturing the semantics of language. With LLMs, we can generate vector representations of text or any other data. It is called vector embeddings, and vector embeddings capture the semantic meaning behind the sentences or words or phrases. Embeddings basically map the textual data to a high-dimensional numbers, and to high-dimensional vectors, where the text with similar meaning produces vectors which are closer to each other in this high-dimensional space. And the third component is similarity metrics, which measures the similarity between vectors. With similarity metrics, we can determine whether the search results are closer to the query terms that the user entered, or whether they are far apart relative to the search query. So we can generate the similarity, we can calculate the similarity between the documents that we have in the database and compare it to the search term vector embeddings generated from the search term and determine which results are relevant to the user. So vector embeddings are, as I said, it's a numeric representation of data, and they represent the meaning and context processed by the large language model. It can be generated from any kind of data, like text, images, audios, or videos. There are different models that support different input formats, or there are also some models that support several input formats and can generate embeddings from different types of inputs. The most important thing to remember is that two objects that have similar semantics will get vector embeddings that are closer to each other in the vector space. And vector embeddings have many different use cases. One of them is semantic search, but it can be also used for text classification, recommendation system, or anomaly detection, or some other use cases. For example, in this diagram that you see, if we imagine for a second that the vector embeddings are three-dimensional vectors, in that case we can visualize the vectors. So we can see that all animals are closer to each other because they are animals. So they are separately, where inside this green sphere we have different animals. They are close to each other because they are all different types of animals. And then we have fruits which are far apart from animals because fruits and animals don't have anything common. But all the fruits are also closer to each other because every item, like bananas, apples, and any other fruit, is fruit. So they are closer to each other. So basically, vector embeddings are a way to convert words and sentences to numbers that capture the meaning and relationship between these words and sentences. Another analogy that we can use is the supermarket. When you go to the supermarket, there is a section for fruits. In this section, you know that different fruits will be closer to each other because all fruits are sold in one space, in one area of the supermarket. And so if you find apple, you know that other fruit will be also somewhere near. But some other items, like magazines, they will be in a different part of the supermarket because they are not related to the fruits. So how does semantic search work? First of all, we have some data in our database represented on the left side. It can be, like I said, it can be text, images, or any other data. We generate vector embeddings from this data. We use an embedding generator with some model that we choose to generate the embeddings. With this, the embedding generator will give us vectors. We store these vectors in some vector store, in some kind of vector database. So we have these vector embeddings persisted in the database. And when we have a request for a search, we take the search query. We again generate vector embeddings using the embedding generator. It's important to use the very same models that we use to generate the embeddings from our database, because if we use another model, then we won't be able to compare the vector embeddings that we have in the database to the vector embedding generated from the search query. So once we have the vector embedding generated from the query term, we use a similarity metric to see which vector embeddings in the database are close to this search query's vector embeddings, and we take the nearest items and get the items that are closer to this search query. We can use either exact nearest neighbors to find the exact matches, or approximate neighbors for approximate results. So basically, the process is that we generate the embeddings from the data that we have in the database. We store these embeddings somewhere, and then whenever the user wants to search something, we again generate embedding for this query term and find embeddings that are closer to this embedding. So let's talk a little bit more about similarity metrics and what does it mean for vectors to be close to each other or far from each other. For example, in two-dimensional space, if we have points, because in two-dimensional space we have just x and y, which is a point, these blue dots represent the vector embeddings from our database. And the orange dot is the vector embedding of the queries that the user entered. So if we look at this, it's easy for us to identify which one is the nearest. You can see that the top blue item is the nearest one to the query embedding. So in two-dimensional space, we can use this formula to calculate the Euclidean distance between points. So if we calculate the distance between all points and between every point and the orange point, we find the smallest distance, and that will be the best result for the query. And in the multi-dimensional space, where we have where the coordinate is represented by a long list of coordinates, not just x and y, we can basically use the same formula, but instead of two members, we will have many members depending on the dimension of the vector. You don't need to implement this formula yourself. All the libraries do this for us. It's just very easy to understand what's going behind the scenes, so I wanted to show it. So yeah, similarity metrics, basically it's a function that takes two vectors as an input and calculates the distance between them. We use this calculated distance to judge how close or how far the two vectors are relative to each other. So we use this to evaluate the vector embeddings that we have in the database relevant to the vector embedding of the query term. There are different similarity metrics. They vary based on speed and accuracy. There is no one-size-fits-all similarity metrics, and the best strategy is to use the similarity metric that the model is that matches the model that we use to generate the vector embeddings. So these are the most common similarity metrics. Euclidean distance is the one that we saw on one of the previous slides. There is also cosine distance and dot product. So depending on the situation, you may use one similarity matrix or the other. So how do we generate the vector embeddings for the data in our database? One option is to use a third-party API like OpenAI. OpenAI has a API and an endpoint for generating vector embeddings. You give it some text, it will return back an array of numbers representing the vector embedding of the inputs. We can basically run the same on Azure OpenAI. There is also Hugging Face inference API. All these options are paid, and they are very cheap, but still they are paid. And also, if you use this means that your data has to leave your system. It goes on third-party server, so you may not be comfortable with that. So another option is to run the model locally. You download the model. You can run it on your server, on your computer. It's depending which model. Some require more resources. Some of them are smaller and can run on a laptop. So For development, for example, you can use Ollama. You can download Ollama, which I will show in a demo. Download a model for Ollama and have the endpoints running on your computer, and then use Ollama Sharp library to access the Ollama API that is exposed by Ollama. Another option is to run the models locally with Semantic kernel. It can run ONNX models. So ONNX is an open format for models. So if you download a model in ONNX format, you can run it with Semantic kernel locally on your machine. And finally, if you are brave, you can also use a library from another language. The good thing is that it doesn't matter which programming language you use to generate the vector embeddings, because as long as you use the same model and same inputs, the model will return the same vector embedding whether you use it from C#, Python, Java, or any other language. So all these options that I mentioned, either the third-party APIs or running them locally, they all have a specific API, depending which one you use. So the API basically differs from one option to another option. So Microsoft released a library called Microsoft Extensions AI, which kind of unifies all the endpoints for generating the embeddings and also many other things. But in this session, I will talk about embeddings. It gives us a unified interface, and there are different implementations for all the options that I mentioned. For example, there's an implementation for OpenAI, there's an open implementation for Ollama, and so on. So as long as you write your code against this embedding generator interface, you can then switch the actual implementations from one to another, and your code that consumes this interface will not have to change, because you are programming against this interface and not against a concrete implementation. So in the demo, we will also see the usage of this library. So once you generate the embeddings, you need to store them somewhere. So here is where the vector databases come in. Basically, we have three major options. One of them is to use a dedicated vector database, like Quadrant, Chroma, or so on. So these are the most well-known vector databases. There are many of them, but these are the most well-known. So vector databases are designed only for working with vector embeddings, for indexing them and retrieving the relevant vector embeddings when you issue a search against the embeddings that you have in the vector database. Another option is to use just relational database. So vector support will be coming in SQL Server 2025. You can try the release candidate if you want. That's what I will be using in the demos today. It's also supported in Postgres with an extension, with the pgvector extension. And also it's available in Oracle if you want to use it in version 23. And the third option is to use the traditional NoSQL databases like MongoDB, Redis, Elasticsearch, and so on. They also support you storing the vector type and running the search in the database. So let's so in this session I will be using SQL Server 2025. It introduces a dedicated type for storing vector embeddings. It can do exact nearest neighbor and approximate nearest neighbor search. It supports all the similarity metrics that I mentioned. It also supports indexing the vector embeddings, and obviously we get all the other features of SQL Server. So basically you you use vector data type like any other type, and you get all the features of SQL Server. So why use SQL Server for storing vectors instead of using a dedicated vector database? Well, first of all, the less different software or the less different databases you use, the less operational maintenance you need. You don't need to synchronize the data from your main database to the vector database. You don't need to care for the backups of the vector database and so on. So basically, everything that you have already working for SQL Server will also work for vector data, for the vector data type. All drivers for SQL Server from all the different languages are already compatible with the vector type. So if you use C# or any other language, you can use the existing SQL Server library to work with the vector type. So if you already use SQL Server, you basically store your vectors with the rest of your data. So this is the syntax for using the vectors in SQL Server. As you can see, there is a dedicated type called vector. You need to specify the dimension of the vector. In this example, it's 3. And once you create the table with the vector column, you can pass the items with the JSON syntax. You can see the insert statement that is inserting the vectors in the database. And then you can also use the vector distance function to find the vectors in the database that are close to the target that you are searching for. So the vector type stores the vector embeddings in an optimized binary format. With older clients, if they have not been updated, they work with vectors like a JSON array, but the newer versions of SQL Server library can take advantage of the binary format and reduce the payload size and be more performant. So let's see a couple of demos how you can do semantic search with the vector type in SQL Server. So I have some data, some 50,000 rows. It's news items from the last 1 or 2 decades. It's in JSON format that I have already imported in the database. Here is the code that handles generating the embeddings. For example, if we use Ollama to generate the embeddings, you can see that I just create a Ollama client. Ollama is running locally on my machine, so I can connect to it. If I want to use OpenAI for generating the embeddings, I just create a client from the library that OpenAI has for C#. And once I have the generator, either the Ollama client or OpenAI client, I pass the generator to this import embeddings function. And as you can see, it's using this interface from the Microsoft Extensions AI library that I used. So this function does not care which API you are using to generate the embeddings. It just needs the implementation of this interface. So this method will read the items from the JSON file, and it just calls the generate async method to generate the embeddings. It will pass an IEnumerable of strings, in this case headlines, and it will get back the vectors and store them in the in SQL Server database. So we can also see the database here. So the embedding column, the last column, it's vector 384, because this is the dimension of the model that I used to generate the embeddings. So the model that I used to generate the embeddings generates the embeddings with the dimension of 384. And I can also show you some data. So here are the headlines, and here are the embeddings. So a large array of numbers with dimension 384. So once we have this data in the database, we can do actual search, and I have different implementations of the search. The first implementation pulls all the data, all the 50,000 rows in memory, and finds the nearest vectors by calculating the cosine similarity here, and taking the top 10 matches. So it will. So when the user enters a query term, what they are searching for, we will again generate the vector embeddings from the text that the user entered, and pass it to the search in memory method. And here we calculate the distance from the query term to the 50,000 items that I have already loaded in memory. I will order by similarity in a descending way and take the top 10 best matches. So let's run this and see it in action. It takes about a minute to load all the records from the database. So as I said, it's the data that I imported is news items from the last 10-15 years. So I will I will search for planes that disappeared. So it will now generate the embedding from these terms that I entered. And we can see that the top 10 best matches are the Malaysia Airlines plane that vanished. You can see it here. So even though it does not say disappeared, it's a match for what I was searching for, because it matches on the meaning. You can also, so the second one is jet that disappeared, so it doesn't have an airplane, it doesn't have plane, but it has jet. So all the, I think most of the matches are matching the search terms that I entered. Now the disadvantage of this method is that I had to load all the records in the database, and maybe for 50,000 items it's more or less okay, it fits in RAM, but if you have millions of records in the database, then you don't want to load all those records in the RAM, because you will need lots of memory, and you can't fit so much memory Yeah, it's better to give the vector embedding of the query term to the database and have the database handle you back the top 10 matches or top 20 or whatever number you are searching for. So for that, the demo will use SQL Server. but first let's see how we can use this vector data type in C#. So as I said, SQL Server stores vectors in optimized binary format, but exposes it as a JSON array for older clients. If you are using Microsoft Data SQL client version 6. I think it should be 11 instead of 1.1, it adds support for the dedicated support for the vector type. So it will use the binary format when decoding and encoding the vector embeddings. So it will have a lot less overhead compared to the JSON text. So if you are using plain ADO.NET, there is a new type for the SQL parameter, and basically you can use this SQL vector type to insert these interesting numbers to the database. If you are using Entity Framework Core, in that case, EF Core 9 uses the JSON compatibility feature that I mentioned, and it requires this library from NuGet. This is an official library from Microsoft. It just adds support for VectorSearch to EF Core. Starting with EF Core 10, support for vectors will be added to EF Core 10. I think it's already available in the RC1 that was released a couple of days ago. So there is no need for extra dependencies if you are using EF Core 10. So in the demo, you will see that basically all you need is that in the onConfiguring method in your database context, you need to specify that you are using VectorSearch. And then you can use the function vector distance to calculate the distance between the query term and the data that you have in the database, and take the top 10 results and returns that back to the user. So let's see this. So here is the second way for finding the results, but in database. Again, this is I pass the vector embedding of the search term and the implementation will just it will order by the 50,000 items that I have in the database based on the vector distance, in this case cosine distance. So it will calculate the cosine distance from the query term to the data in the database, ordered by the distance, and takes the top 10 items. So the less the distance, the closer the item in the database is to the vector embedding that I generated from the search terms. So let's run it again. So now it will run it 2 times, one in memory, the second time in the database. I will use the same term for searching. So we can see that in the database, these are the same results, but the difference is the search happened in the database. So the database returned back the 10 matches that are near to the search term, and we can see the actual SQL statement that was executed by the database. If we do this once again, I will type the same term. And here we have this I queryable. So this is the SQL statement that was generated by Entity Framework 9, and that was executed on the database. So we can see that it's selecting the vector distance, and also the ordering is done based on the vector distance between the embedding column and between the parameters that we passed to this query. So we can see the exact same query here. So this variable here, this is the vector representation of plane that disappeared that I typed. So these are the numerical values generated by the LLM model for that phrase. And here I'm just ordering this. The order by is done based on the vector distance between the embedding column and this vector variable that is declared here. So if I run this select statement, you will see the exact same 10 results that we saw in the demo right now. So this is the distance. The less the distance, the more relevant it is to the query. So this is the same SQL generated by EF Core. Okay, so we saw how to generate embeddings, how to store them in SQL Server, how to find the nearest embeddings compared to the relative to the search term, and the next thing is vector indexing. So indexes in the databases are important, as you probably know, because indexes help us to speed up the operations in the database. Without the indexes, the queries can become slow as the number of rows grows. The difference between vector indexes and the so-called traditional indexes is that when you are doing a where statement or join or some other SQL statement, when you add an index, it doesn't affect the search results. You get the same results, but faster. So it does not change the results that you get back from the database. It only speeds up, hopefully, the selects. But in case of vectors, the index works in a different way. Basically, all the operations that we saw before in the demos, all the searches were exact nearest neighbors. It means that when we asked the SQL Server to return the nearest neighbors, it needed to calculate the distance between the query term and every 50,000 records in the database. This means that as the number of rows in the database increases, the number of calculations is also increasing linearly, because if you have 1,000 items, it needs to calculate 1,000 distances. If you have 1 million, it needs to calculate 1 million distances. And this becomes slower and slower as the number of rows is increasing. And it's very computationally heavy. Basically, there's a linear relationship between the number of rows in the database and number of computations. So another approach is to use approximate nearest neighbor, which trades off a bit of accuracy for a huge increase in performance. So it will So the ANN, which stands for approximate nearest neighbor, it will do the calculations based on the index only on the subset of data and reduce the computational burden, but the results will be approximate. They may not be the exact nearest neighbors, but will be approximated results. So when you create an index on a vector column in the database, it does not matter whether it's SQL Server or any other vector store, the results that you get back will be approximated. That's how vector indexes work. So this is to illustrate the number of operations in exact nearest neighbors. It's linear and it's logarithmic when it's approximate nearest neighbor. So approximate nearest neighbor will find similar vectors without searching all of them. It will offer significant computational improvement. It will be a lot faster. It will use a lot less resources, but the results will be approximate, like not 100% exact, but still very good. So how do we evaluate the approximate nearest neighbors? How do we evaluate whether the results returned by the ANN search is good or whether it's not so good? We can evaluate it based on so-called recall. So recall is a measure that tells us how many nearest neighbors returned by the ANN search are the true nearest neighbors. So let's say that all these black crosses are the embeddings in our database. The red cross is the query term that we are searching. The ones in the light gray, I think you can't see the difference there because of the screen, but the 5 in this circle around the red cross, they are the true nearest neighbors. So if you use exact nearest neighbors, you would get these 5 results that are around the red one. And let's say that if you use approximate nearest neighbor, you get back the 5 from the orange or yellow or the yellow section. In this case, we can see that the intersection between these two results is the 4 black items, which are in the gray area. So this means that from the 5 nearest neighbors, which are the true nearest neighbors, the approximate nearest neighbor search gave us the 4 ones, because the 4 is the intersection. Yeah. So in this case, we can say that the recall is 4 out of 5. So it means the recall is 80%, because 4 is 80% of 5. Yeah. So ANN will cost a little bit in results, so the accuracy will be a little bit lower, but it will be much faster and still usable in real-life scenarios. For vector indexes, there are different algorithms or different strategies. There is inverted file with flat compression. There is HNSW. And there is DiskANN, which is available in SQL Server 2025 and in other products of Microsoft. This was developed by Microsoft Research. It's high recall, so the recall that I explained in the previous slide. So DiskANN has high recall, like 95, 98, so basically almost the true nearest neighbors. It performs better than the other indexing algorithms that I mentioned. It's open source, so you can see the implementation on GitHub if you want to. And the vector search function that is available also in 2025 in SQL Server. If you use this table valued function, VectorSearch, it will use the index as long as the index in the database, obviously. So to create the vector index, you just need to run this statement. Instead of create index, we use create vector index, and we specify the column which contains the vector embeddings, and also what type of metric we want to use. In this case, cosine similarity, and the index type, the only supported value is DiskANN. So I have already created the index in the database. It takes some time, so I have created it already in the database. So now we can see the third version of the search, and because it's a table valued function, I had to use the SQL query instead of writing a link query. I had to use the SQL query method and pass the SQL statement directly. So the SQL statement, we can also see it in Management Studio. So in the previous example, we were doing order by vector distance, but now we are calling the vector search function. We pass the table, we pass the column, and the query vector, and the metrics that we want to use. So if I run this now, it will run approximate nearest neighbor search in the database and return the top 10 results. Now, because the data size in the database is very small, it gives exactly the same 10 results. But now it uses the index, so we can see that the actual index is used. So here we can see that it used the vector index DiskANN that we have in the database. So with this approach, we can run the same query with Entity Framework Core, and if we can also compare the times. So we can see that the in-memory search took about 100 milliseconds. The database took about 300 without an index, and with the index it takes a bit more than 130, a bit more than 100. If I run it again, it will be faster. So now, now the one using the index in the database is the fastest, and it's less than 50 milliseconds. So it's a lot faster than the one without index. And there is one other demo that I want to show. So currently, all the demos that we saw, all the demos, we are using this model. I will now switch to another model. So I have a second database here. It's storing the embeddings generated from this other model. This model generates embeddings with dimension 1024. You can see it here. So the difference between these two models is that this model, this snowflake model, is multilingual model. So this means that the previous model supported only English. This model is supporting several languages apart from English. So so why would we use a model that supports different languages? So yeah, because this model supports different languages, it means that the embeddings that are generated, for example, from German text is closer to the embeddings generated from other terms that are closer in semantic model, for example, in English. This means that we can enter the search term in German, and it will find results in English records that I have in the database that more or less match the meaning of the German text. So it's not as good as English, searching for an English phrase in the English database, but it's still I had the password somewhere. I forgot that I needed this. Yeah, it was somewhere in I have it in my phone, but not here. I will create a hotspot. Oh, it's connected. So if I now translate this to German and I enter it here, it will now generate vector embeddings from this phrase, this German phrase. The first time, because I switched the model, it now leads to Olama needs to load the model in memory. So we still have this missing Malaysian Airlines flight as number 2. And here also. So these are not the same results that we had when searching English text in English database, but still more or less relevant to the German phrase that I entered from the data in English in the database. So yeah, that's all that I wanted to talk about. The demo is available on GitHub. This is the QR code for the GitHub repository. And I hope you found this interesting, and you can check the demo and my other projects on GitHub. If you have any questions, I can try to answer them. If not,